Okay, so today we're going to cover roughly section 1.1 in the textbook, which is on statements and conditional statements. Okay, and most work in mathematics deals with statements. But already we should be asking, well, what do we mean by a statement? Right, so maybe you remember from taking linear algebra that it's really important in mathematics to have very precise definitions, because otherwise you don't know what you're talking about, right? You don't really understand something until you can define it really precisely and understand what that definition means. And once we've both defined, I don't know, linear independence in the same way, then when I say, oh, this set of vectors is linearly independent, you know exactly what I'm talking about. So definitions are incredibly important in mathematics. So it stands to reason that the first thing we'll do in this class is we'll make a definition. So here's the definition. A statement is a declarative sentence that is either true or false, but not both. Okay, and a statement is sometimes called a proposition, depending on the context or the textbook. So I'll use the word statement, but if you see something like, I don't know, the phrase propositional logic or something, there the word proposition means the same thing as statement. Okay, so this definition has basically two parts, right? What is a statement? Well, first of all, it has to be a declarative sentence. That means that it's not a fragment. It means it's not a question. It means it's not a command. So it's a full sentence that's declarative. So it would end with a period, for example. The second part of the definition says that this declarative sentence has to be either true or false, but not both. That doesn't mean you can know whether it's true or not, but it needs to be a sentence that has one or the other truth value and not both. In particular, this means that any variable that appears in the statement has to be defined. Okay, so let's look at some examples. Okay, so first example, if I look at the expression 3x plus 2. Okay, so that is a mathematical expression, but it's not a statement because it's not a sentence, right? 3x plus 2 is not a sentence. So this is not a statement. I have all these colors. Let's do this in color. Right, since it's not a sentence. It's not a declarative sentence. It's just a fragment. Okay, perhaps a bit better. 3x plus 2 is less than 12. Okay, now this is a sentence. 3x plus 2 is less than 12 is a sentence. This sentence happens to be written entirely in mathematical symbols, but it's a sentence. However, 3x plus 2 is less than 12 is not a sentence that I can say is true or false unless I know what x is. Right, so this is if I read it out, 3x plus 2 is less than 12, that's a full English sentence, but it's not a statement. So it is a sentence, but not, I mean, it's even a declarative statement, but it's not a statement. Since we cannot evaluate whether it is true or false, since we don't know what x is. Okay, here's another one. There is a real number x such that 3x plus 2 is less than 12. Okay, so now we're talking. This is a full English sentence, and perhaps you can even tell, hopefully, that it's a true sentence. So I could evaluate that it was true and it's not false. This is a true statement, but even if it were false, it could still be a statement, right? So we'll see some examples in this case. So this is a statement. And then independent of it being a statement, it happens to be true. Since if you take the real number 0, 3 times 0 plus 2 is less than 12. So there does exist a real number x such that 3x plus 2 is less than 12. Okay, another example. Let's take a look at this sentence. X plus y squared equals x squared plus y squared. Again, this is a sentence. This is a sentence written entirely in mathematical symbols, but if you read it out, x plus y squared equals x squared plus y squared, that's a sentence. However, it's again not a statement because we can't evaluate whether it's true or false because we don't know what x or y is. Okay, so this is not a statement. Since we can't evaluate. Okay, but I bet many of you looking at this think, oh, that's a false statement. My reaction to that is also that if I see someone write this down, I think, oh, that's false. Why do we think it's false? Because there is a related statement that is definitely false. Okay, so maybe we'll enumerate this in a sublist. Here's a sentence. For every, let's say for all real numbers, x and y, x plus y squared equals x squared plus y squared. This is a sentence and it is a statement because I can tell you it's false because if you take x and y to both be 1, for example, it's not true that x plus y squared equals x squared plus y squared. So this is a statement, but it's false. Since, e.g., you could let x equal y equals 1, and then the left side will not equal the right side. Okay, so a really important point here is that if you mean this sentence in this class, you need to write this sentence. Because one of the points of this class is to learn how to communicate mathematics. If what you mean to assert is for every real number x and y, x plus y squared equals x squared plus y squared, you need to write that down. If you write down this instead, then you have not written down the same sentence. You have not made, in fact, you haven't made any statement at all if you write down just x plus y squared equals x squared plus y squared. You haven't said what x is, you haven't said what y is, and as a result, you haven't written a statement. So in previous math classes, even the more conceptual ones like linear algebra, your professor probably was not emphasizing communicating mathematics extremely clearly. Sort of, as long as you got the idea down on paper, that's more or less what they were grading. Okay, but in this class, you need to be extremely precise with what you write. Okay, let's write down a related statement. What about this statement? There exist real numbers x and y such that x plus y squared equals x squared plus y squared. This, again, is a statement. It's a full English sentence that you can say whether it's true or false. And this statement is true, right? Because, for example, you could take x and y to both be 0, or you could take x to be 0 and y to be 2. Right? So this is a statement. And it is true. You can take x and y to both be 0 to show that this statement is true. Okay, so as you can see, the difference between this sentence and this sentence is that they're completely different. One is true and one is false. So if you're trying to communicate mathematics, you need to write the thing that you mean. And again, in your previous classes, you maybe could have gotten away with writing this top line, but if you're trying to communicate mathematics clearly, you can't just write that top line to mean either one of these things. Okay, so hopefully this explains, this set of examples explains this definition, what a statement is. But generally in mathematics, the big question that you ask, you don't just make statements just to make statements, right? We can construct lots of statements, but the big question is, how do we decide if a statement is true or false? This is the big question. Statement is true or false. Okay, so hopefully on this previous slide, there were 3 statements, right? And I said, oh, the first 2 are true, and the first one is true, the second one is false, and the third one is true. And hopefully you believe me. But there can be many, many more complicated statements, right? I've just made some extremely simple statements here. And a big part of this class is learning how to decide and communicate whether or not a statement is true. Like I said, generally, this is a general rule. Generally, in mathematics, to establish that a statement is true, what you do is you write a mathematical proof. Okay, so a mathematical proof is a sequence of logical deductions written in complete sentences that establishes the truth of a statement. More or less, that's what a proof is. And we will get lots of practice writing proofs in this class. It's one of the major goals. In these video lectures, I will try really hard to write really careful proofs, at least at the beginning, so you have a model for them. Okay, you will also have a model for proofs in your textbook. So those are also written very carefully, and in the other textbook that I linked in the syllabus, and lots of other places, but those are the main places that you should look. Okay, of course, when I say generally, like for example, this last statement, there exist real numbers x and y such that x plus y squared equals x squared plus y squared. For that statement, in order to show that it's true, you just need to give an example, right? Because to establish that that statement is true, you just need to cook up one set of real numbers, x and y, such that x plus y squared equals x squared plus y squared. But generally, if you're asked, if you're trying to show that a statement is true, generally you need to write down a proof. Okay, to establish a statement is false, you can just give a counterexample. Okay, so this often happens, but even from this first slide, it shows why I said generally, right? So for example, for this second statement, the one that's false, it's true that what I did is I gave a counterexample to show that the statement is false. But if I want to show that this last statement, is false, I would need to show that it's not possible to pick any real number. I mean, okay, so it's true. So obviously I can't, but if I wanted to show that this was false, if I thought it was false, I would need to show that it's not possible to pick any real numbers satisfying this property, which would require a proof because it would need to cover all possible real numbers x and y. Okay, so this generally thing that I've written here is sort of just a general guideline. Okay, and of course, as I said before, the kinds of statements that we care about in mathematics, even in linear algebra, as you've already taken, are much more complex statements than the statements that I gave on the first slide. So generally, to establish whether they're true or false will require a lot of reasoning, a lot of tools, a lot of definitions, and putting things together, right? So in order to learn how to do mathematics, we need to learn how to discover proofs, construct them, and then write them down so that other people will understand our logic. Right? And this is how mathematical knowledge advances over time in the big picture. more mathematicians discover more true things. They prove them so that other mathematicians will also be able to see that they're true, and then you can build on top of that, right? So before Newton, right, nobody knew the fundamental theorem of calculus. Before Euclid, we didn't know that the sum of the internal angles of a triangle is 180 degrees. I'm actually not sure if either of those people prove those two statements, but the point is that mathematical knowledge progresses over time when mathematicians discover new true statements and provide proofs so that other people can also see that they're true. Now, to a sort of a microcosm of that will be things like homework exercises, which lots of people already know are true. That's why they're homework exercises. But for you, the homework exercises may be statements that you didn't know were true before you took this class. So you need to figure out, why is this statement true? How can I understand why the statement is true? And how do I communicate that clearly? Okay, so let me now talk about slightly more interesting statements that we'll try to discover and we'll try to prove. So for the rest of this lecture, I don't want you to be too concerned about if you can follow every step in every proof, because we haven't learned how to prove anything yet, right? So we will learn lots of proof techniques and such as this course goes on. Right now, I just want you to think about this without thinking in too technical details, okay? So before we write a proof, oftentimes we make conjectures. In other words, we try to guess at what kinds of things might be true, and then we try to prove them. How do you do this? Generally, this is done through exploration. So what do I mean by exploration? It means thinking about some small examples or trying to prove it. I mean, once you have some small examples, trying to notice some kind of pattern, maybe thinking about related ideas, maybe collaborating with other people. This is all very general stuff because mathematics is just one place where you can use problem-solving skills. But for example, whoever it was, I said Euclid, might not be, whoever it was that proved that the sum of the internal angles of a triangle on the plane is 180 degrees, how can you go about proving that, right? So the sum of the internal angles of any triangle is 180 degrees. Here's a great mathematical statement. Somebody needs to discover this and then prove it. How could you go about discovering this? Well, how you would go about proving this is by thinking about a lot of different triangles, right? So maybe the first thing you do is you notice, oh, well, in an equilateral triangle, right, you sort of mess around with it geometrically and you discover, oh, well, all of the angles here are 60 degrees. This is probably something that could be done. You think, okay, well, therefore 60 times 3, that's 180 degrees. The internal angles are 180 degrees. Right, then maybe you draw a right triangle, right? Maybe you have a protractor, right? So you're trying to draw these things really accurately. You're like, okay, well, that's true for equilateral triangles. I wonder if it's true for right triangles. And then you get a protractor, right? So you've drawn this really accurate right triangle. You measure this angle, you measure this angle, and you notice, oh, well, the sum of the internal angles is 180 degrees. Okay, well, there are other kinds of triangles other than equilateral and right triangles, right? So then you start just drawing random triangles. Maybe you do some measuring, and you notice that you get this weird phenomenon. Then you go about thinking, okay, how could I prove it? Note also that, I mean, I kind of like this example because as I stated it, the statement is not true. You think it's true, but really, maybe I should say in the Euclidean plane or something, in Euclidean space. Because if you imagine that you're on the surface of the Earth, right? and you start at the North Pole, and then you walk in a straight line down to the equator, and then you make a 90-degree turn, and you walk in a straight line along the equator for like, I guess, a quarter of the circumference of the Earth. Then you make another right turn up, and you walk straight to the North Pole. You'll see that you'll also make a right angle with where you started at the North Pole. So the internal angles of this triangle, it's a triangle, has 3 straight sides on the surface of a sphere, is 270 degrees. Right? So actually, if you don't say that you're working on the plane, if you're working on the surface of a sphere, this theorem actually wouldn't be true. So in fact, explorations like this can lead you to more sophisticated geometric concepts like curvature. So somehow measuring angles inside of triangles tells you about the curvature of a surface. Okay. Like I said, don't worry if you don't understand anything. I also haven't proved anything. I'm just trying to give you some motivation here. But let's now move into something where we can have some hope of exploration, for which I'll need the following definition. Okay, so an integer larger than 1 is said to be prime What's a prime integer? A prime integer is one that can't be written as a product of 2 smaller positive integers. This is one way to define prime. And this will be our definition of prime in this class. Okay, so you probably know what a prime number is, right? Like 2, 3, 5, 7, 11. Now let's try some exploration and just try to look for some patterns. Okay, so what I'm going to do, this is maybe something that someone did a long, long time ago, is let's look at n, and let's look at the number 2 to the n minus 1. Okay, reasonable enough to try to understand. Okay, so let's start with n equals 2. When n is 2, 2 to the n minus 1 is 4 minus 1, that's 3. When n equals 3, we get 2 cubed minus 1, that's 8 minus 1, that's 7. 4, we get 16 minus 1, that's 15. 5, that's 32 minus 1, that's 31. 6, 64 minus 1, 63. 7, 128 minus 1, 127. 8, 256 minus 1, 9, 5, 12 minus 1. Okay, so even just in this simple example, there's lots of things to notice about these numbers, right? Like, for example, this is not so profound. Every number in the second column is odd, right? So that's actually quite easy to prove once you know the definition of odd, which we don't know the definition of odd yet, or we at least haven't made it in this class. But what I want to notice is, let's try to understand the times when n is prime. Okay, so when is n prime? So n is prime 2, 3, 5, 7. Okay, but let's also look at the primes in the right-hand column. So 3 is prime, 7 is prime, 15 is not, 31 is, 63 is not, that's divisible by 3. 127 is prime, 255 is divisible by 5, and then 511 kind of looks prime, but it's not. It's 7 times 73. You can verify that. So there's sort of an interesting pattern happening here. Hopefully what you notice is somehow it looks like when n is prime, 2n minus 1 is prime. Also, it looks like when n is not prime, 2 to the n minus 1 is not prime. And those are 2 separate statements. Okay, so from this data, maybe we can make the following conjectures. Okay, so let's call this one conjecture 1, although in your notes it's called conjecture 5. Suppose n is prime, then 2 to the n minus 1 is prime. This is one conjecture. Conjecture 2, suppose n is not prime, then 2 to the n minus 1 is not prime. These are both mathematical statements, right? And it's not clear whether or not they're true, right? Because so far what I've done is I've checked 8 numbers, the numbers 2 through 9. And for these 8 numbers, they did not give a counterexample to conjecture 1 or to conjecture 2. Let me call these conjecture A and conjecture B, just so that it's not so confusing when you compare it to your notes. Okay, so how could we prove or disprove these conjectures? Well, one way that you could disprove one of these conjectures is by finding a counterexample, right? So what I could do is I could generate a lot more data and see if at any point one of these conjectures failed, right? So I can even do the next couple. So 10, that's not prime. 2 to the 10 minus 1, that's 1023. And this is going to be divisible by 3, I guess. So this is 3 times 341. So both conjecture A and conjecture B, so far we don't have a counterexample. Okay, let's look at 11. 11 is prime, and you get 2047. And then you play around with this for a little bit, and you realize that it's 23 times 89. So 11 is prime, but 2 to the 11th minus 1 is not prime. So this shows that one of these conjectures is false. Which one? It shows that this first conjecture, conjecture A, is false. Because I found an n that's prime where 2 to the n minus 1 is not prime. So that's good, right? Like, as I said one slide ago, in general, if you want to prove that a statement is false, oftentimes you can give a counterexample, and now we know that conjecture A is false. Okay, what about conjecture B? Well, what I could do is I could continue writing down data, right? So 12 is not prime. 2 to the 12th minus 1, that's 4,095. That's not prime because it does it by 5. And I could just keep on going. And I can guarantee you that no matter how many numbers you check, you're not going to find a counterexample. But if you just keep on checking examples, that is not that convincing, right? Maybe you have to get till n is like 1 million before you find a counterexample, so that conjecture B would be false, but it would take a lot of data to get there. If you want to prove that it's true, you need to prove that it works for every possible non-prime integer n. And there's no way to do that just by giving examples, because there's infinitely many non-prime integers. So in order to show that conjecture B is true, which it is, we need to provide a proof. We need to provide a line of deductive reasoning such that somebody who reads it will believe us. So let's prove conjecture. Proof of conjecture B, which is true. Okay, so this will be our first proof that we're writing in this class. So I'll try to write it as clearly as possible, as I always will in this class. Okay, so the first thing to say is that proofs should be written in complete English sentences in this class, right? So of course, if you're in another country, if you're in Russia, proofs are written sometimes in complete Russian sentences, although just because of the way the world is at the moment, also lots of proofs are written in English, even in Russia. If you're in France, a proof could be written in complete French sentences. In this class, a proof is written in complete English sentences. Okay, there can be mathematical expressions in a proof. Things like the expression 3x plus 2 is less than 12, or 3x plus 2 can appear in a proof if you want to talk about 3x plus 2, but it needs to appear inside of a sentence. Okay, so it should be written in complete English sentences. It should make sense if you read it, right? It's like someone's giving a complete argument. That means it needs to be properly punctuated. It needs to be properly capitalized, right? Mathematics is not just a string of equations, which is maybe the impression that you get in calculus. So here's my proof, okay? So let's suppose that n is not prime. Right, I'm trying to prove that if n is not prime, then 2 to the n minus 1 is not prime. Well, what does it mean to say that n is not prime? Well, to be prime means that you can't be written as a product of two smaller positive integers. So to be not prime means that you can be written as the product of two smaller positive integers. Okay, so by the definition of primeness, then there exist positive integers a and b that are less than n, such that n equals a times b. Okay, notice that that last sentence I wrote is a complete sentence that involves some mathematical symbols in it. If you read it, it reads as a complete sentence. Then there exist positive integers a and b less than n, such that n is equal to a times b. Note also that it's important that I say what I mean by a and b. By a and b, I mean positive integers. Okay, now here comes kind of the magic. Let's let x equal 2 to the a minus 1 and y, let's say 2 to the b minus 1. And I'm going to let y be equal to 1 plus 2b plus 2 to the 2b plus 2 to the a minus 1b. Okay, now it shouldn't be all that clear to you why I picked x and y to be this way. So oftentimes when you present a proof, you sort of give the reader the answer. In order to figure out what to let x and y be, somebody needs to play around with trying to understand how to factor 2 to the n minus 1. Okay, so let's let x be this number and y be this number. Okay, then let's look at x times y. What is x times y? It's 2 to the b minus 1 times 1 plus 2b to the b plus 2 to the 2b plus, it goes to up to a minus 1b's. Okay, now I can distribute. So this is 2 to the b times 1 plus 2 to the b plus up to 2 to the a minus 1b minus 1 plus 2 to the b plus up through 2 to the a minus 1b. Right, all I've done is just distributed this 2 to the b minus 1 over the long sum. Okay, now I can multiply m. So here I get 2 to the b plus 2 to the 2b plus 2 to the a minus 1b plus 2 to the ab. I've written an extra term there. Okay. Minus still this long sum. And now what do you notice? There's lots of cancellation here, right? So this term cancels with this term. This term cancels the next one. This one will cancel with this one. So we're left with just two terms left over. This is equal to 2 to the ab minus 1. And a times b is n. This is equal to 2 to the n minus 1, period. Okay, notice that this is also a complete sentence that involves a long string of mathematical expressions. Right, but essentially the sentence says then xy equals this, which equals this, which equals this, which equals 2 to the n minus 1. So this is an okay sentence, but I needed all the sentences at the beginning to set this sentence up, right? I can't start my proof with just xy equals this because, right? I mean, I can't start my proof here because I need all the stuff before. Okay, now what have I done? I have factored 2 to the n minus 1 as a product of x and y. Okay, so let me wave my hands a little bit, but since b is less than n, Therefore, x, which is 2 to the b minus 1, is less than 2 to the n minus 1. Okay, hopefully you can believe that. Like I said, in this first lecture, don't get too bogged down in the technical details. I'm just trying to give you an overall idea. Okay, also, since AB is n, which is bigger than A, it follows that B is bigger than 1. Okay, because I multiplied A by B and I got something bigger than A. So B must have been something bigger than 1. Right? Therefore, x, which is 2 to the b minus 1, is bigger than 2 to the 1 minus 1, because b is bigger than 1, which is 1. So sort of by the exact same reasoning as before, this means that y is less than xy because x is something bigger than 1. And xy is 2 to the n minus 1. Okay, so this reasoning here, I'm using some stuff that we haven't proved in this class because it's the first day of class, but hopefully it's all believable to you. Why did I do this? I want to make sure that x was less than 2 to the n minus 1 and y was less than 2 to the n minus 1, because I'm trying to prove that 2 to the n minus 1 is not prime, which means I need to show that it can be written as a product of two smaller integers. So therefore, 2 to the n minus 1 can be written as a product of two smaller integers. So 2 to the n minus 1 is not prime. And so I've shown that if n is not prime, then 2 to the n minus 1 is not prime. And so I've proven conjecture B. And generally, when you complete a proof, you inform the reader that your proof is done by putting a small box in the corner. This thing is called, you can look it up, this thing is called a halmos. After Paul Halmos, it's sometimes called a tombstone. And actually this came, believe it or not, this came from the publishing world. So if you've ever read a magazine article in a real live magazine, which hopefully you have, maybe in like 20 years when I'm teaching this course, none of the students will have ever seen a physical magazine. They'll have only swiped it through magazines on their iPad. But if you read like a physical magazine, oftentimes the articles end with like a little black box. So actually mathematics borrowed this idea from magazine publishing essentially. Okay, so now that we've proven this conjecture, we can call it a theorem because we've proven it. Right, so let's go back here and let's call this theorem B. And let's call this the proof of theorem B. Okay, so a theorem is a true mathematical statement that has been proven. Okay, this proof is actually the best kind of proof because not only does it show that this theorem is true, it even gives you a computational tool. It even tells you how to factor 2 to the n minus 1 if you can factor n. Right? If you can factor n as AB, then you know that 2 to the b minus 1, or symmetrically 2 to the a minus 1, is one of the factors of the number. Right? So going back to this table, how could we factor this quickly? Or this quickly, rather. This is 2 to the 9th minus 1. And 9 is equal to 3 times 3. So 2 cubed minus 1 is a factor, which is 7, which is how you could easily factor 511 once you know the proof of this theorem. Okay, so first proof in the class, like I said, there's some details which we haven't really figured out because we haven't learned anything about prime numbers yet. I'm just trying to give you an overview of some mathematical things which in my opinion are more interesting than the things that appear in section 1.1 of your textbook. Okay, now let me give you another proof about prime numbers, which was proven by Euclid over 2,000 years ago, and is probably the most classical result about prime numbers, and it has an extremely beautiful proof. Okay, so if you go to any math professor at any university in the entire world, and you ask them, oh, can you prove that there are infinitely many primes? Every single one of them will give you this proof. There are, of course, other proofs of the fact, but this is a proof that you should never forget because the technique is so nice and so beautiful, and it was proven over 2,000 years ago by Euclid. Here's the result. There are infinitely many prime numbers. Okay, so when you graduate from this illustrious institution and they walk you across the stage and you pick up your diploma that says mathematics on it, they should not let you graduate unless you can recite this proof, because nobody should ever forget this proof. Okay, how can you possibly prove that there are infinitely many prime numbers? Here is the extremely beautiful proof due to Euclid. Okay, suppose that there are only finitely many prime numbers. Right? Let's see what would happen if there were only finitely many prime numbers. What we're going to show is that if there are only finitely many prime numbers, then something ridiculous will need to be true, which is obviously not true. Which means that there can't possibly be only finitely many prime numbers. This is called proof by contradiction. It's a technique that we'll learn later. But for now, I just wanted to, don't worry again too much about the technical details. Just try to understand the overall flow of the proof. Okay, so suppose that you only had finitely many prime numbers. Let's list them. So let P1, P2, up through Pn be a list of all the primes. We could do this if there were only finitely many. Okay, now let's let M be the following number. P1 times P2, the product of all the P's plus 1. Okay, now notice that M is not divisible by P1 because M is a multiple of P1 plus 1. Right, so notice that M is not divisible by P1 since it is a multiple of P1 plus, maybe let's say it is one more than a multiple of P1. Right, and all the multiples of P1, they occur spaced out by P1, right? All the multiples of 7 have a difference of 7, right? 7, 14, 21, 28. If you add 1, you're never going to get a multiple of 7 because it's not far enough away. Okay, so similarly, M is not divisible by P2 or P3 or any of the primes. Similarly, M is not divisible by P2 up through Pn. Okay, now, we have not yet proved this theorem, but you can prove that every integer, we will prove in fact, every integer larger than 1 is either prime itself or can be written as a product of primes. Okay, so by a theorem from later, every integer greater than 1 is either prime or can be written as a product of primes. Okay, well, m is definitely bigger than 1 because it's some positive number plus 1, which means that it's either prime or a product of primes. But also, no primes divide m because we listed all the primes, p1 up through pn, and none of them divided m. So notice that m is bigger than 1, and no primes divide m. Therefore, by the theorem that we didn't prove, m itself must be prime. Okay, but m is bigger than every prime on our list because it's actually a multiple plus 1 of every prime on our list. Which means that if p1 up through pn were all of the primes, m would be a bigger prime that we haven't listed yet, which means p1 through pn can't possibly be all of the primes. So, but m is larger than p1 up through pn, so we have found a new prime. This contradicts our assumption that p1 through pn was a list of all primes. So if there were only finitely many prime numbers and we listed all of them, then there was one that we didn't list, which is a contradiction. Therefore, there can't be finitely many prime numbers, which means that there are infinitely many prime numbers. So our assumption was false. There are infinitely many primes. Okay, so this is a really, really beautiful proof. It just has a very elegant quality to it. And if you go back, you can actually look in the elements. This is basically the proof that Euclid gave. He gave a slightly more geometric version, something about lengths, like of rectangles, but it boils down to this proof. And now we've proven this very abstract fact. Now we know that there have to be infinitely many prime numbers. Okay, so why did I give you these two theorems today? Well, first of all, hopefully, even if we don't understand all the details, we can understand that conjecture A was false, that theorem B was true, and that the fact that there are infinitely many prime numbers is true and even proven. So even on the first day of your first real math class, you can understand these things. But it turns out that related to these things, these very elementary things, are really, really, really hard, unknown mathematical truths. Even on day one, we can list an extremely hard open question that nobody knows the answer to. Okay, so why all this about primes on the first day? Okay, so we know now that if n is not prime, 2 to the n minus 1 is not prime. If n is prime, then 2 to the n minus 1 may or may not be prime. Okay, so a prime of the form 2n minus 1 is called a Mersenne prime, after the French monk and mathematician Mersenne. Okay, we also know that there are infinitely many prime numbers. That's due to Euclid. So what that gives us is it gives us infinitely many possible Mersenne primes, right? Every time you have a prime number, of which there are infinitely many, you can pop n into this number, 2 to the n minus 1, and this gives you another candidate for a Mersenne prime. So each gives a candidate for a Mersenne prime. Right, so you can plug in 3, you get 7. You can plug in 11, you get 1023. You can plug in some humongous prime number, right? A prime with like about, like, I don't know, 2 to the 10,000 minus 1. That, sorry, obviously 10,000 is not prime, but I think maybe 10,001 is prime. So 2 to the 10,001 minus 1, that may or may not be prime. Here's the thing that's not known. So open question. Are there infinitely many Mersenne primes? This question is not known by modern mathematics. And you, as a first day of a real math class math major, can understand this question. Probably in order to prove or disprove, okay, in order to prove or disprove whether or not there are infinitely many Mersenne primes, we'll take some really fancy mathematics that we haven't invented yet, I guess. Another thing that I'll mention is that there's this thing called the Great Internet Mersenne Prime Search. It's called GIMPS, where you can donate CPU clock cycles to testing whether candidate Mersenne primes are prime or not. And at least as of when I wrote these notes, which was actually last autumn, I should check, but I doubt there's been progress since then. The largest known prime number in the world, like just the largest known prime number, is a Mersenne prime. So this was discovered by the Great Internet Mersenne Prime Search. The largest known prime is a Mersenne prime. So this is like a good way to generate large primes. It's 2 to the 82,589,993 minus 1. So this, it turns out, is prime. By the way, based on what we proved in this class, now you also know that this number must be prime. It's not that obvious that the number is prime, but if this whole thing is prime, then the exponent must be prime. And this thing has almost 25 million digits. Okay, so if you could prove that there are infinitely many Mersenne primes, I suspect it's an extremely difficult question. Probably you could write a paper that you get featured on like Slate or Quanta or whatever. You'd be very famous for like, probably for a long time. Okay. So this first lecture, again, I want to give you sort of an interesting introduction to some interesting mathematics, not some of these more banal statements that appear in section 1.1 of your textbook. But this is sort of like a grandiose overview. Of course, starting in the next lecture, we will get down to the nitty-gritty and start from the very basics so that we can build up all the technology to learn some of the fundamental tools of mathematics and to be prepared for our future math classes. All right.